Hello, welcome to the lecture on radio properties of clusters of galaxies. I am Ruta Kale from the National Center for Radio Astrophysics of the Tata Institute of Fundamental Research, and I am going to describe the radio properties of clusters of galaxies. And in this background you see the giant meter wave radio telescope, which is one of the main instruments which we use to find the radio properties of clusters of galaxies. I will start with an overview of galaxy clusters and then come to the point as to why we look at galaxy clusters in radio bands, and continue with first the properties of radio galaxies in galaxy clusters, then about radio halos and radio relics, and then about cluster mergers and how they are connected to radio halos and relics, and then what we hope to do in future with the upcoming different radio telescopes in the world. And in the end I will summarize a few resources to gain more knowledge about radio properties of clusters of galaxies. So, clusters of galaxies are basically part of this large scale structure which we call as the cosmic web. So, if we look at our universe on the largest scales, we see that the structure of the distribution of galaxies turns out to be of like a cosmic web, and galaxy clusters are actually the nodes of these intersecting filaments. So, these bright portions in the simulation that you see in the background here, those are galaxy clusters, and they are the most massive gravitationally bound systems in the universe. They contain total masses of the order of 10 raised to 14 to 10 raised to 15 solar masses, of which most of this mass is made of dark matter, about 80 to 85%, and then a few percent is in galaxies and 10 to 15% in the diffuse matter which pervades the space between these galaxies, and it is called the intracluster medium. So, when we talk of radio bands in the electromagnetic spectrum, the radio band comes at the long end of the wavelengths, which is shown here, and galaxy clusters as they look in X-ray emission are shown in this image here, and they look like large extended sources of X-rays, which is basically the emission from the intracluster medium. And the other view shown here of galaxy clusters is in optical band, where you see mainly the starlight. The stars are basically parts of all these galaxies that you see in this image, and that is taken in the optical bands or the visible band. And now we want to move all the way to the long wavelengths and try to see what we can learn from looking at these objects in radio bands. For this lecture, when I describe radio bands, I will usually refer to the frequency range of 100 to 10,000 megahertz. So, the intracluster medium is going to be an important component while I describe the radio properties of galaxy clusters. So, let me introduce that to you first. So, intracluster medium is mainly composed of thermal plasma, which is of temperatures of the order of about 10 raised to 7 to 10 raised to 8 Kelvin. It has core densities of the order of 0.1 to 10 raised to minus 3 per centimeter cube, and the radiation mechanism for this thermal plasma is called thermal bremsstrahlung, and that is what leads to the clusters being extended sources in X-ray bands. Here is an example of a galaxy clusters as it of a galaxy cluster as it looks in X-rays. However, what is not seen in this X-ray image are these components which are basically relativistic particles and magnetic fields. So, relativistic particles are typically termed as cosmic rays, and the other component which is typically termed as a non-thermal component are magnetic fields, and the magnetic fields in galaxy clusters are known to be of the order of 0.1 to a few microgauss. So, these relativistic particles and magnetic fields are not detectable in most observing bands. Now, what makes them observable in radio bands is the synchrotron radiation. So, if you have electrons of energies of the order of GeVs and they are moving in magnetic fields of the order of a microgauss or so, you will find that from clusters of galaxies or such plasma, you will find emission detectable in radio frequency bands. Now, typically when we observe in radio bands and study a source, the most important characteristic of the source that we would like to measure is the spectrum of the source. So, here you can see a plot which is a schematic. On the y axis is the flux density and on the x axis is the frequency, and the blue curve shows a power law like spectrum which is typical for radio sources or sources that emit by synchrotron mechanism. And that is described by a power law which is basically the flux density shown by S proportional to the frequency to the power of minus alpha, where this alpha is denoting the spectral index. The synchrotron spectrum, basically when electrons lose energy by synchrotron emission, this effect of this energy loss on the spectrum is to make it steeper and steeper. So, what I mean by steeper is basically that this power law like straight line will become, the slope will become steeper in this log-log plot, and you will see an emission spectrum which looks like this red curve. So, as you can see here, as we go towards lower frequencies, we are likely to see the emission from such synchrotron mechanisms better than going to higher frequencies, because as soon as the source basically becomes less energetic, it is going to still stay detectable at low frequencies and go out of your detection limit at higher frequency. So, coming to what mechanisms are of interest to observe in clusters in radio bands. Now, as I said earlier, components such as magnetic fields and relativistic charged particles are only detectable at radio bands. Therefore, we would like to look at galaxy clusters in radio bands. Magnetic fields in galaxy clusters are basically the field lines along which the plasma is driven, or the charged particles basically are tied to these magnetic field lines as they move. Therefore, magnetic fields are crucial in transporting energy within galaxy clusters, and thus they are important for studying any physics of galaxy clusters. The other important part is that we would like to probe fundamental physics of particle acceleration. So, the other non-thermal component that I mentioned, which was the relativistic charged particles, how did they come to gain such energies to reach relativistic speeds? That is an open question, and looking at galaxy clusters allows us to probe fundamental physics of particle acceleration. And then, as it is true of any astrophysical system or typical astrophysical systems, galaxy clusters are unique laboratories to study plasma under such extreme conditions which are not possible to be created on Earth. And therefore, we would like to look at clusters in radio bands to study all of these. Let us begin the first part on radio galaxies in clusters. So, why are radio galaxies in clusters of interest? Radio galaxies occur everywhere in the universe, not only in galaxy clusters. However, galaxy clusters are the densest environments that these galaxies see around them, and therefore, there are special effects specific to this environment which the galaxy experiences, and therefore, they are excellent media to study the interaction between the radio galaxies and the dense environment. So, the galaxy can be affected itself by the surrounding medium, and in turn the galaxies can affect the intracluster medium. So, among all the galaxies in a given galaxy cluster, the brightest cluster galaxies are the galaxies that experience the densest environment. They are the galaxies which are located at the centers of the cluster, and which is where the intracluster medium is the densest. And the special location of these brightest cluster galaxies at the bottom of these potential wells of galaxy clusters makes them bigger than all the other galaxies in the cluster itself. So, these are extremely massive galaxies. Among the most massive galaxies in the universe are found at centers of galaxy clusters, and they experience this environment of the dense intracluster medium, which in turn activates the accretion at the supermassive black hole, which leads to bipolar jet emission. So, a typical radio galaxy looks like this, where you have the central galaxy seen in this blue color here, and the red emission is the radio emission. So, there are bipolar jets emanating from the supermassive black hole at the center of this galaxy, and you can see the emission extending far beyond the optical emission from this galaxy. So, these are called jets from this supermassive black hole, and what they form when they reach far away, go to distances far away from the black hole itself and the galaxy, are the lobes, which are these extended structures seen in red color. So, the way the central galaxies affect the intracluster medium is as follows. So, it is shown in this other figure, where you have the intracluster medium in X-rays shown in white to blue light, and the red color shows the radio emission from this galaxy. As you can see here, the jets and the lobes of this radio galaxy have carved out cavities in the intracluster medium. So, the brightest cluster galaxies, when they have such jets and lobes, they end up heating the surrounding medium, which is via the mechanical work done on this medium because of their expansion. And this is a crucial factor in heating the core of galaxy cluster, and this forms a important component in what is called as the feedback mechanism at cluster cores. Apart from the cluster center itself, other galaxies across the cluster can also produce jets and result in this jet lobe like radio emission. Galaxy shown here in this image is moving in the direction shown by the blue arrow, and the black arrows show the direction of the pressure experienced by this galaxy because of the external medium. So, this radio galaxy is moving in the intracluster medium, and the external pressure is exerted by the intracluster medium on it. So, depending on the pressure that this radio galaxy experiences as it moves in this dense medium, the amount of bending could change. So, the most in the situation where the bend is really starting all the way from the central part of the galaxy, one calls them head-tail radio galaxies, and those with lesser bent jets are termed as narrow and wide-angle tail galaxies. So, we will look at head-tail galaxies because they are typical of they are typically occurring in cluster environments. So, this is an image of a head-tail galaxy, where you see the optical image of the galaxy, where basically the supermassive black hole is where the jets are starting at the supermassive black hole and then continuing as a tail behind this galaxy. This is another spectacular example of a head-tail galaxy. It is called 3C129. It is also a galaxy which is moving in the intracluster medium, and its jets are bent to the extent that you see them like a head-tail galaxy with a long flow of this radio emission. So, when head-tail galaxies move in the intracluster medium, you can find them to appear as if they have a single-sided jets. Here are several examples of such head-tail radio galaxies which were studied with the GMRT. In contours, you will see the radio emission from these galaxies, and it is overlaid on the optical image of that galaxy. So, there are a number of configurations that can happen in depending on our line of sight, the projection along our line of sight, and the motion of the galaxy. Another thing of interest about radio galaxies in clusters are what happens to these radio emission which is emitted in the form of jets and lobes after the supermassive black hole stops accretion and thus producing or injecting any fresh material into the jets. So, that is the situation when one calls that the central engine is switched off, and what you get is a dead or a remnant radio galaxy. So, the central engine at the active galactic nucleus at the supermassive black hole is switched off, and the jets and the lobes of this radio galaxy passively evolve in this dense intercluster medium. In this image here, you see X-ray emission from this cluster shown in red color. The green and yellow are showing the galaxies in this cluster, and the blue emission is showing the radio emission. And what is peculiar about this source is that it is a dead radio galaxy. What you see at 1.4 gigahertz or 1400 megahertz is this tiny little filamentary structure here, which is actually emission which is bright enough to be detected at 1400 megahertz. However, this entire emission that you see in blue color at 325 megahertz was hidden at high frequencies, and low frequencies allow you to detect these low energy plasma, which is important to study the evolution of these relativistic plasmas in intracluster medium. As we go along, I will refer to these dead or remnant radio galaxies and their importance in the generation of cluster wide radio sources, which I will be describing in the next part. The other important emission from galaxy clusters which is associated with cluster galaxies is called radio mini halo. Radio mini halos are basically radio sources that surround the central elliptical galaxy, and they occur mainly in cool core clusters. In this image, you see the X-ray emission in pink, and in white contours you see the radio emission. So, this morphology seen in the contour plot is unlike a standard jet lobe like morphology of a radio galaxy, and this is typical of what is called a mini halo. So, they are nearly circularly symmetric sources which surround this central elliptical galaxy, however, are unlike typical radio galaxies. To explain the emission of such morphology and on the scales of 90 to 500 kiloparsec sizes around the central galaxy, it has been proposed that minor mergers, or when galaxy clusters undergo mergers with other galaxy clusters, a minor merger can result in the oscillation of the cool core of the galaxy cluster, and that can lead to reacceleration of the relativistic plasma that exists around that galaxy and lead to such sources which are termed as mini halos. So, in the next part of this lecture, we will come to sources which are on much larger scales that we described until now, and are not associated particularly with any one galaxy in the galaxy cluster. In this part, we will be looking at sources called as radio halos and radio relics. These are sources which are associated with the intracluster medium itself and not with individual galaxies. We start first with radio halos. Radio halos, as you can see in this image, are extended radio sources which have sizes of the order of 700 kiloparsec and as large as 2 megaparsec. In this image, a radio halo is shown in white contours, and in pink is the X-ray emission from this cluster. And as you can see that this source extends the entire extent of the X-rays and probably also beyond the X-ray emission. So, this is called a radio halo. It has a radio power at 1.4 gigahertz in the range of 10 raised to 24 to 10 raised to 26 watts per hertz, which is similar to bright radio galaxies. The peculiar thing about these radio halos is that they are extremely low surface brightness sources, and their surface brightness at 1.4 gigahertz is in the range of 1 to a few microjansky per arc second square. So, what this means is that we need extremely sensitive telescopes to detect such sources. The origin of these sources is proposed to be in turbulent reacceleration of mildly relativistic electrons in the intracluster medium. So, I would like to come to the fact that why do you need to reaccelerate relativistic electrons when there are sources like the radio galaxies described in the previous parts, which can emit relativistic electrons and uh, put them in the intracluster medium. So, if such a source were available, could it not accumulate relativistic electrons in the intracluster medium to give rise to a radio halo? Let us look at the physics of transporting relativistic electrons from the cluster core to cluster outskirts. So, in this schematic, the circle represents the size of a cluster, and at the center is this energetic relativistic electron, which is created in the jets of radio galaxies. And now this is emitting synchrotron emission, and it is losing energy on time scale of the order of 10 raised to 7 years, which is the typical synchrotron lifetime of relativistic electrons. To transport this relativistic electrons to as far as the outskirt of the cluster, it will go by a process called diffusion, and the time scale over which it can diffuse to distances of the order of the size of the cluster is more than 10 raised to 9 years. So, there is this discrepancy between the synchrotron lifetime and the diffusion time. So, by the time the electron, the relativistic electron diffuses out to cluster outskirts, it would have lost energy and therefore would not emit synchrotron emission. So, you cannot make radio halos by dispersing relativistic electrons that are created at a single source like a radio galaxy. So, what you need to invoke is a mechanism which can create relativistic electrons all over the cluster, and this process is referred to as in situ production of relativistic electrons, and the processes for creating such electrons, relativistic electrons, are proposed to be in turbulent reacceleration. We come to the other cluster scale diffuse radio source called radio relic. Radio relics are arc-like or elongated radio sources that have sizes in the range of hundreds of kiloparsec to 2 megaparsec. They are polarized to a few to 30% level. In this picture here, you see X-ray emission from the cluster in red color, and the green shows the radio emission detected with the GMRT at 330 megahertz. What you see at the outskirts of this cluster are the two arc-like sources, which are termed as double relics, and this cluster shows an elongation in X-rays which is in the direction of the location of these radio relics. Now, such relics appear as double relics as shown in this figure, or they could appear also as single radio relics. In this example is a galaxy cluster X-ray emission shown in blue, and the red color denotes the radio emission, and you can see this single elongated filamentary source at the outskirts of this cluster, which is a single radio relic. The elongated and arc-like morphologies of these single or double radio relics and their location at the peripheries of clusters in the direction of the elongation of the X-ray emission and their polarized nature indicates that these are tracers of what are called as shocks in galaxy cluster mergers. From the radio properties of radio relics, one can derive the speeds at which the cluster merger has happened and the strength of the shock. So, radio relics are termed as tracers of cluster merger shocks, and the Mach numbers of such shocks have been measured to be in the range of 1 to 3. From here, we will now move on to the next part, which is about cluster mergers and beyond. Both radio halos and relics that are described so far have been found to be associated nearly exclusively in clusters which are undergoing mergers. So, just like objects such as cars collide, galaxy clusters collide too, and in fact cluster mergers are the most energetic collisions in the universe, which involve gravitational potential energies of the order of 10 raised to 63 to 10 raised to 64 ergs. And the phenomena that result in the generation of relativistic electrons energetic enough to be detectable in radio bands are a result of cluster mergers. So, in this part we will look at simulations of galaxy cluster mergers and visualize the effects which a cluster merger produces in the intracluster medium, which lead to reacceleration of particles that we detect as radio halos and relics. In this cluster merger simulation that we are going to see, what will be shown is dark matter in the cluster, and in the second panel you will see the X-ray emission from the cluster. So, this simulation basically evolves dark matter particles and the gas particles which are moving in this gravitational potential of the dark matter. Let us see the simulation. So, in the left panel you see the dark matter particles that collide, and their physical property is that they are collisionless particles. So, they keep moving in according to what gravity defines, whereas what you see in X-rays is a gas which is weakly collisional, and what difference it makes to be weakly collisional is that it can produce effects such as shocks and turbulence in the intercluster medium. So, in X-rays you will find signatures of shocks and turbulence in the form of distortions in the X-ray emission from a merging galaxy cluster. Now, these shocks and injected turbulence can result in reacceleration of particles, which is basically proposed to be the origin of the relativistic electrons that emit the radio emission that is detected as radio halos and as radio relics. In the next slide, we will see a simulation in which we will see X-rays in the left panel, and we will see actually the radio emission in the second panel. So, here in color on the you can see X-rays, and the contour levels actually define the radio emission. In the other panel you see the synchrotron emission in blue color, and the recipe that led to this emission of synchrotron origin is basically based on the observations of radio halos and has been put into a simulation to reproduce the effects that we see in actual clusters. From this simulation, it can be seen that cluster mergers can be powerful enough to inject shocks and turbulence that can result in cluster-wide radio emission. Now, coming to cluster mergers and beyond. So, beyond the cluster mergers themselves is this whole large scale structure, which looks like this filamentary structure, the nodes of which are galaxy clusters, the bright points in this figure, and connecting these nodes are the filaments. And in this plot, the color scale actually shows magnetic fields that are expected to pervade this large scale structure in the universe. The magnetic fields are of the order of a few microgauss at the cluster cores. As you go to outskirts of clusters, these magnetic fields become weaker, and as you move on to the intergalactic medium, which is basically the diffuse medium that pervades these filaments, the magnetic fields can reach levels of nanogauss or even weaker. And the next challenge in front of us is the detection of this radio emission that pervades the whole cosmic web. And that is what we expect to do with the next generation of radio telescopes, among those being the upgraded GMRT and the square kilometer array. So, we come to the fourth part, which is about the resources available to access the fundamentals of all the physics that goes into studying galaxy clusters in radio bands. Here are some of the textbooks which are listed. These include the 2 volumes of high energy astrophysics by Longueur and the physics of fluids and plasma, a textbook by Arnab Raichaudhuri. The next resource I would like to point out are the review papers. The information in this presentation in the introduction came from a bunch of these review papers. Among these are the physics of cluster mergers by Craig Sarrazin, magnetic fields in galaxy clusters by Govoni and Ferretti. There are several recent reviews on cosmic rays in galaxy clusters. For example, cosmic rays in galaxy clusters and their non-thermal emission, and an overview of physics that we can learn by studying merging galaxy clusters, which is a review by S.M. Molnar. And here are some selected papers that are listed on this topic of radio emission from galaxy clusters. I would like you to look up these papers, and as well as the references that are listed in these papers will point you to the development of this field as a research field across previous several decades. These papers listed here are from journals of astronomy, and not all of them may be freely available. However, an open resource for papers and reviews is the archive.org, and you will find the latest papers and reviews all listed on the archive. And all of these resources can be accessed on the internet, and the books you will find in the libraries. So, you are welcome to find out more about radio properties of galaxy clusters. Thank you.